So this is our third tutorial. Let's start. Here we'll discuss the following topics, which are linear transformations, transformations, rank nullity, and kernel range. Those are the topic of our discussions. So for this question, here the linear transformation is from R2 to R2, and the question is, so there are four transformations given A, B, C, D. We need to see which are linear from those. So if we see the first linear transformation, means it is a functions from V to W to vector spaces which preserve linear structure. So the meaning of this is T of, suppose there are two vector, and if we take linear combinations C1 V1 plus C2 V2, and if we apply the transformation or the function T, it should give us C1 times T1 V1 plus C2 times, sorry, here only T, C2 times TV2. So we can see that linear transformations, those actually preserve additive and scalar multiplication. Addition, scalar multiplication. And if we take the linear combination 0 times b, then we can easily, from here it follows that T of 0, this must be 0. So in option A we can see T of the 0 vector is 0 comma 0, which is, if we apply the formula, this will give 0 comma minus 5. Therefore T of 0 is non-zero. Hence A is not a linear transformation. So this is not a linear transformation. This maybe let me write T1, T2, T3, T4. So this will imply T1 is not linear. Now option B, here, so here T2 of 0 comma 0, this is 0 comma 0. So 0 goes to 0, there is no problem. 0 vector goes to 0. Now if we check other properties, for example, we check the scalar multiplication is preserved or not. So suppose you can see 0 comma 2, this belongs to R2. So suppose V is this. Now if we apply T of V, which is same as 0 comma 2 cube, it is 0 comma 8 by this formula. But this is same as 0 2 times 0 comma 1. So if we so this is same as 2 times p dash. Suppose 0 comma 1 is p dash, then t2 of p dash, this is same as 0 comma 1 cube, which is 0 comma 1. So v equal to 2 times v dash, but we can see that t2v this is not equal to 2 times T2 V dash. Hence, that is mm, uh, here we can see that scalar multiplication is not preserved under this transformation. So again T2 is not linear. Not linear. Next option is C, which says T3 A comma B goes to 0 comma A plus B. Is defined to be 0 comma A plus B. So again 0 goes to 0, there is no problem. Let us see if addition and multiplication are preserved. So take two vector, one is V1 equal to A1 comma V1 and V2 equal to A2 comma V2. We can see that T3 of V1 plus V2, this is same as, we can see the addition of those two things V1 plus V2, this is pointwise addition, that is A1 plus A2, coordinate wise V1 plus V2. So if we put the addition and if we apply this definition star, so star will imply this is same as 0 comma first component plus second. So A1 plus B1 plus A2 comma A2 plus B2. But this is same as, you can see that T3 of V1, so T3 of V1 plus T3 of V2, this is same as 0 comma A1 plus B1. Again we are applying definition, individually we are calculating this, plus T3 of V2, again by definition V2 is this, so T3 of V2 will become 0 comma A2 plus B2. So it is now clear that T3 of, so this is same as 0 comma A1 plus B1 plus A2 comma B2. So those two are same, that is T3 preserve addition, T3 of V1 plus V2 is same as T3 V1 plus T3 V2. Clearly T3 is linear. Sorry, this is not done. We need to check if it preserves scalar multiplication. So take C from the scalar field R here. So if we again apply T3 times CV1, which is same as T3 times CA1 comma CV1, coordinate wise multiplication, scalar multiplication, and by definition this is same as 0 comma CA1 plus CB1, but this is same as take C common, A1 plus B1, that is C times T3 V1. Therefore T3 preserved scalar multiplication also. Therefore T3 must be linear. So option C is the correct answer. But we can again see that D is incorrect. Why? Because for option D you can see T4 0 comma 0, this will give A which is 0, and now 1 plus 2 to the power B, B is also 0, so it is same as 0 comma 2, which is non-zero, right? So T4 is, by the same reason, T4 is not linear. Not linear. Okay, now let us see question number 2. So here t is t be a function, given function, and t is defined in this way. T of ABC, this is same as this combination. Then what can be said about range space and null space? Their dimension and uh, an element from the range space will look like which of these. So let me say something. We know that dimension of range space, this is called rank of T, this for this transformation, and dimension of null space is called nullity of T. And what are range space of T? Range T, this will look like T applied on those vector. Here V will look like A, B, C. T of V, where V belongs to the domain vector space capital V. For example, V is F3 here. And kernel T or null space, kernel T, it is alternatively denoted as null space of T. This is same as all V. So clearly this is a subspace of range uh, codomain. T is a map from V to W, this linear transformation we are considering. So it is element from V such that T of V equal to 0. All those elements of the vector space V which maps to 0 under the transformation T. And kernel T is subspace, kernel T or null space T, it is a subspace of V. Those are some basic thing about range kernel and what are the definition of rank nullity of T. So back to this question, we need to see what are the possible. So if we need to find the range space, what a range space will look like for this example. So given T of ABC of this form, so we can write a better approach will be write this as, so let x, y, z, this belongs to range space, range T. Okay. So then T of ABC will be x, y, z for some ABC, which is equivalent to solving this equation. Equivalent to solving the equation a plus 2b minus c equal to x, that is, maybe write in this way, b plus c, which is y, a plus b minus 2c, which is z. X, y, z. So we need to solve this system of equation, that is, we need to solve this system of equation a plus 2b minus c equal to x, b plus c equal to y, and a plus b minus 2c equal to z. So find ABC for which this holds. So this is equivalent to solving this matrix equation. So we know how to solve those kind of equation. It is 1 2 minus 1, 0 1 1, 1 1 minus 2, and we'll put xyz here. So we take the matrix and put it in augmentation matrix form, and again apply row reductions. So the first row reduction will be R3 minus R1, so that we can cancel this 1, right? So this will give us 1 2 minus 1, 0 1 1, 0 minus 1, minus 2 plus 1, which is minus 1, x y, and z minus x. Now R2, sorry, R3 plus R2, so that we can cancel this, right? So R3 plus R2, and also R1 minus 2 R2. We should perform those operations. So R1 minus R2 R2, this operation will give us 1 0 and minus 1 minus 2, which is minus 3, and x minus 2y. This row is unchanged, and now this row R3 plus R2, this will cancel, minus 1 goes to 0 and minus 1 also goes to 0. This becomes z minus x plus y. So solving the problem becomes, it is equivalent to solving this equation. So this equation means it is again a, this is 0 times b, a plus 0 times b minus 3 times c, this equal to this, and similarly b plus c equal to y, and similarly 0x 0a 0b plus 0c, which is 0 on the left side, but this is equal to this. So only the solution exists. This is possible if and only if, so such a solution exists if and only if z minus x plus y equal to 0. So something belongs to null space. We have assumed x, y, z belongs to null space. This is only possible when this becomes 0. Okay, so this becomes 0. So this becomes 0. It is equivalent to say that z equal to x minus 1. Okay, so x, the answer x, y, z belongs to range of t if and only if z can be written as x minus 1. And we can see those are actually free rows. Those are those contains the element 1, that is leading 1 in the row echelon form. Therefore there are no restrictions. Those can be anything, x minus y and y. So for something belongs to null space, it will automatically imply that there is a relation, that is z can be written as x minus y. That is, alternatively we can write x comma y comma z such that z is same as x minus y. This is the range space. Okay, so this matches with this option D, right? Z equal to x minus 1. Answer is D. And also we can see that what is null space for this. So again the same thing, what is the null space? Null space is equivalent to solving find xyz, find maybe abc in this case, such that a times this abc equal to 0 vector. So this is equivalent to say null space means it is equivalent to solve 1 0 minus 3 0 1 1 0 0 0 times this abc equal to 0. So from here we can see that rank of this matrix, if we denote R to be the row echelon form, then rank of the matrix A, which is same as rank of R, which is same as 2. Clearly it can be seen as 2. Therefore, range space, that is rank of T, the transformation, it will also be 2, because A is the matrix representation of the transformation. And similarly, nullity, we can see that what rank nullity theorem says, that rank plus nullity should be dimension of the domain. That is dimension of V, this is same as rank of the transformation plus nullity of the transformation. So nullity of T, here dimension of the codomain, dimension of the domain, this is 3, and rank is 2. So 3 minus 2, which is 1. That is, nullity can be obtained from the subtract rank T from this dimension V. So nullity should be 1, rank is 2. But here nullity is given as 2, which is false, because we obtain nullity is 1. And similarly, dimension of range space, this is given as 1, but we obtain this will be 2. And this is also incorrect, because it should look like z equal to x minus y, but here z equal to x plus y, right? For example, if we choose x to be 1, y to be 1, then z will becomes 1 minus 1, which is 0. But this pair does not satisfy this equation, because z is 0, which is not same as 1 plus 1. So C is also incorrect because of this, right? Okay. So question number 3. Here T be a linear transformation from R2 to R3. It is given of this form. And we need to find what is T applied on 8, 11. So let us see what is the coordinate of 8, 11. That is, first thing is like this: 8, 11. We want to express 8, 11 as linear combination of some element. That is 8, 11. We want to write it as x times 1, 1 plus y times 2, 3. If we can write this, then by linearity we will obtain the value of 8, 11. Just apply t and use the property of linearity. So this is equivalent to solving this equation. So need to solve the following equation. So this is same as, again we can write this as x plus 2y equal to 8 and x plus 3y equal to 11. So it is equivalent to solving this kind of equation. 1, 2, 8 and 1, 3, 11. So again apply. So we can say this, right? A times some x equal to b. Those are b. The matrix, this is b, and this is the matrix A. We have again written augmented matrix. Okay. And now we'll again apply row reduction. So after applying some row reduction, that is multiplying r on the both sides, something r is not the correct thing, something like p, because we are denoting r to be row echelon form. So p times a, it will becomes identity x and it will become pb. But we know that a is invertible will give x equal to A inverse P, right? So this PB must be same as A inverse P, that is P is same as A inverse. Applying P is same as applying A inverse, right? So we'll get the solution X. So let us see what will be application of A inverse on this P. We need to find that. That is X is same as A inverse P. We need to find that. So R2 minus R1, this row operation, this will give me 1 to 8 and 1 gets 0. 3 minus 2 is 1. 11 minus 8 is 3. Again apply row operations which give me, that is R1 minus 2 R2, so that these two get cancelled. 1 0, 8 minus 6 which is 2, 0 1 3. Therefore the solution X is same as A inverse P, which is same as 8 comma 3, right? So we obtain that 8 comma 11. This thing can be written as this. This is the first component X, and this 3 is the second component Y, right? Because we are initially we are solving for this X, and this X is same as X comma Y. The notation X means this is X comma Y. Okay, so 8 comma 11, this is same as 8 comma 1 comma 1. 8 times 1 comma 1, sorry, it is not 8 comma 3, it is 2 comma 3. Some mistake, this is 2 comma 3, right? Okay, so 8 comma 11 is same as 2 times 1 1 plus y is same as 3, because x is same as x comma y. We are denoting that. So 3 comma 2 comma 3. So you can see that this matches. 3 times 2 is giving 6, and 6 plus 2 is 8, and 11 can be written as 2 plus 3 times 3. If you can guess this combination, then it is okay, but if you cannot guess, then we need to solve in this way. So putting those entries, so you want to express this 8 comma 11, this 8 comma 11 as linear combination of this 1 comma 1 and 2 comma 3. That is we are doing. Those are justification, but it can be avoided. So now what is the equation for T? T, applying T is same as, okay, so T is given as T of 1 comma 1 is 102. So T of, so by linearity, T of 8 comma 11, this is same as 2 times T of 1 comma 1 plus 3 times T of 2 comma 3. But 1 comma 1 applied, T applied on 1 comma 1, this is 102, and this gives us 1 minus 1 4. 102, 1 minus 1 comma 4. But there is coefficient 2 here, and here the coefficient is 3. So this is same as 2 plus 3, which is 5, 0 minus 3 minus 3, 4 plus 12, 16. So the answer should be 5 minus 3, 16. 5 minus 3, 16. So the answer is A. Now question number 4. In this question, T is given as this. So T of 1 1 is same as 1 minus 2. T of 2 3 is same as minus 2 comma 5. So we need to, the question is like this, we need to find the matrix representation actually. Okay, matrix representation with respect to the basis E1 comma E2, those standard basis, because T of x means we need to find what is the value of T of x1 comma x2. It will look like some matrix times x1 x2. So this x is not correct because, sorry, this x is correct, but this x should be transposed because we apply t on this type of things, but here it is 1 by 2 matrix, but this is 2 by 1 matrix, right? So this should be like this, exact. Okay, so to t we need to find the matrix A. So we need to find what is the, so we need to find T of 1 comma 0 and T of 0 comma 1. If we can find this, maybe this is the correct notation. T of 1 comma 0, T of 0 comma 1. We need to find those two things. So let us, it is similar to the previous things, that is 1 comma 0. This need to be written as linear combination of those things 1 1 2 2 3. We need to write 1 comma 0 as linear combination of 1 1 comma 2 3. And similarly we need to write 0 1 as linear combination of those. Instead of writing this, let me see what is, we are trying to x comma y, we are trying to write x comma y as linear combination of 1 1 2 3. So let me solve in this way. So this is equivalent to, so applying row reduction, this will gives R2 minus R1 1 2 x 0 1 y minus x. Again R1 minus 2 R2 1 0 x minus 2y plus x, that is sorry, minus 2x plus x minus 2y minus 2x, that is plus 2x. So this is same as 3x minus 2y, and this becomes 0 1 y minus x. So left side becomes row echelon form. Therefore from here we can see that if the matrix, if a comma, sorry, what do we need to see? Yes, so if we put 1 0, if we initially put 1 comma 0 here, then one comma 0, this can be written as maybe an easier, there should be an easier way to write this. T of x is same as a comma x. So okay, so let me solve in this way. Okay, so 1 comma 0, this can be written as linear combination of this form. So initially if we put x to be 1 here, y to be 0 here, then we can see that these two will give me the combination will be like this. So first one will be 3 times 1 minus 2 times 0, which is 3. So 1 comma 0 is same as 3 times 1 comma 1, and second one will be 0, y, value of y is 0, value of 1 is 1, so it is minus 1. 0 minus 1, so this is minus 1 times 0. Sorry, this is 1 1 and this is second thing was 2 3. So 1 comma 0 can be written in this form, right? So this whole thing is matching. This is minus 1 actually, minus 1, because similarly 0 comma 1, this also can be written as, again, we instead of 1 0 we'll put x equal to 0, y equal to 1. If we put this, then the second b, that is the second thing, this will becomes 3 3 times 0 minus 2, which is minus 2, and the value of x is 0, value of y is 1, so this is 1. So this can be written as minus 2 times 1 1 plus 1 times 2 3. This minus 2 comes here, this 1 comes here, right? Okay. So this is now almost done. So again we'll see what is t applied on those two things. So t applied on 1 0, this is same as 3. I should write in row form, so this is actually not a right way to write. This is 1 comma 0 and this becomes 1 comma 1 minus 2 comma 3. Just we are applying transpose, because this can be written as that combination, then if we apply transpose, this also can be written as this combination, 2 comma 3. So if we apply t on the both side, then t of 1 0, this will becomes 3 times t of 1 1, but t of 1 1 is same as 1 minus 2, so 3 times, so t of 1 0, this is same as 3 times 1 1. 1 1 goes to 1 minus 2, and 2 3 goes to minus 2 comma 5. Minus 2 times 1 minus 2 plus 1 times minus 2 comma 5. So this is same as 3 plus 2, which is 5, then minus 6 minus 5 minus 11, and this is minus 2 minus 2 minus 4 plus 4 plus 5, which is 9. So if we put in, so it is clear now, right? The matrix should be 5 minus 11 and minus 4 comma 9. We just apply transpose on those two things, because matrix representation will be like this. It is same as 5 times e1 that standard base is minus 11 e2, and this is same as minus 4 e1 plus 9 e2. So we just put this combination as columns. So this should be the correct answer. 5 minus 4 minus 11 9. 5 minus 4 minus 11 9. So option should be B. Answer B. Actually, I have done lots of things here. We don't need to do that much. It is enough to often. Maybe this can be solving an easier way, but This you can use this approach also. For this question number 5, the transformation, there is a linear transformation. So first V is the space of polynomial function of degree less equal to n. So what are explicitly V can be written as this: a0 x cube plus a1 x square plus a2x plus a3, sorry, its dimension of p is n, sorry, degree of p, highest degree is n, so it should start from a0 x to the power n plus a1 x to the power n minus 1 plus an x to the power 0, such that ai are from scalar field f. This is the explicit way of writing the polynomial functions, space of all polynomial function whose degree less equal to n, and T be a linear transformation from V to R. T is linear transformation from V to R, and it is, so any polynomial will look like this. So we may denote this as Px, the polynomial Px, and T applied on Px, this gives the sum of coefficient, right? Sum of coefficient means, so here the coefficient of Px is a0, a1, an. So it T of Px will give this transformation. Now the question is, what is nullity of T and what are the basis of null space? So we assume something from the null space. Let this polynomial Px belongs to null space of T, right? Then T applied on Px should be 0. This is same as, equivalent to saying T applied on Px is same as this, right? So if we put a0 plus a1 up to an, this becomes 0. Alternatively, we can say that a0 can be written as minus a1 minus a2 dot dot minus an. So those are actually equivalent. Null space, Px belongs to null space if and only if this holds. A0 is of this. A0 is the a0 take the form a0 equal to minus a1, that is sum of other coefficient, and add a negative sign. So what will be a basis for this? From here it is clear that null space, so let me write null space of T, this is same as all a0 plus a0 x to the power n plus a1 x to the power n minus 1 plus an x to the n x to the power 0, which is n, such that null space will look like those polynomials such that the coefficient a0 okay, maybe it is better to write n here. For our n can be written as this minus a0 minus a0 minus a1. Just I am writing for my, okay, so we can see that n can be written as minus a0 minus a1 up to minus an minus 1. I was writing for my convenience, okay, but we can see, So this can be written as like this. Instead of n, I am putting those signs. So it will take this from a0 x2 and ai are from real number, satisfying this relation. So a0 x to the power n plus a1 x to the power n minus 1 plus n minus 1x. Now instead of n, I can put minus a0 minus a1 up to minus n minus 1, right? And there is 1. So this will look, this will take this form such that ai are from real number, right? Not real number, here the scalar field is f. It can be real, complex, whatever. But if we write, this also can be written as take a0 common, then it becomes a0 x to the power n minus 1 plus a1, this would be minus 1 plus a1 x to the power n minus 1 minus 1 plus n minus 1 x minus 1 such that ai belongs to it. So from here this is clear. If we choose the coefficient a0 equal to 1 and a1 an minus 1, those are any real number, right? So we can choose in our case. For example, if we choose a0 equal to 1 and a1 a2 those n minus 1 equal to 0, if we choose this, then we'll get x to the power n minus 1 belongs to null space of T, right? So in a similar manner, we can see all those x to the power n minus 1, x to the power n minus 1 minus 1, all those things, x minus 1, all those things belongs to null space. And moreover, any element can be written as linear combination of those things, right? There are n possibilities. There is n element, n polynomials, and any polynomial from the null space can be written as linear combination of those n elements. Therefore, this is the basis of null space. Those are linearly independent. We can easily check those are linearly independent because we can just see that here degree is n, here degree is n minus 1, and here degree is 1, right? So whatever linear combination if we choose to vanish that combination, this must imply all those coefficients become 0. So those are linearly independent and it is spanning the whole null space. Therefore, this is a basis. So this is a basis, and moreover, from here it is clear that nullity, dimension of null space, this is same as, we can say basis contains n element. Here degree 1, degree 2, degree n minus 1, degree n. So the corresponding degree will give n elements. So dimension of null space is n, and nullity, this is actually called nullity. Then what will be rank of this thing? Rank of T, this is same as dimension of the dimension of V, which is polynomial space in this case, minus nullity. But what is dimension of this polynomial? It is generated by x to the power n, x to the power n minus 1 up to 1. So we can see there are n minus 1, 0 up to 0 degree, right? We are counting from, this is x to the power 0. So counting from 0, x to the power 1 up to x to the power n minus 1, x to the power n. So there are n plus 1 vector which are independent and which actually generates this polynomial space. So from here it is clear that dimension of V is n plus 1. So dimension of V n plus 1 minus nullity is n, which is 1. So rank should be 1, nullity should be n. So nullity is n minus 1. This is completely wrong. Nullity of t is 1. This is also wrong because nullity is n actually. This is wrong because nullity is n. Right? And this is not a basis for null space because we can easily see that t of x is non-zero, because by definition t of x is same as coefficient, sum of coefficient. But here the coefficients, it can be written as 0x to the power n plus up to dot dot plus 1 times x plus 0 times 1. So the coefficient, sum of coefficient will be same as 0 plus 1. 1 only appear once. So this is 1, which is non-zero. So x does not belong to null space. So this is not possible. So only the possible, and we have computed the only possibility is this. So this is the correct answer. We can easily discard those type of thing easily, because instead of computation we can easily see that range space contains, range space is the whole R. So dimension of range space should be 1, because what is the dimension of R? Not R here. Yes. What is the dimension of R? The field F should be R. Otherwise, this question does not make any sense. So dimension of the whole range space is 1, because it is a onto map. Right? It will take whole R. For example, if you take this, some C belongs to R, then this C is same as T times C. T of C. T applied to C, this will give you C. Because this C can be written as C times 1. C times 1 plus, plus other thing are 0. X, coefficient of x square, those are 0. Right? That is T of C will be C. So this map is onto actually. Onto, so range space will, range of T is whole R. Therefore dimension of range space, which is rank should be 1. So from here also we can, instead of finding null space, for this question it is easy to see what is range, and we can easily conclude rank should be 1, and rank 1 will automatically give us nullity will be n, because the vector space has dimension n plus 1. As rank is 1, the nullity should be n. So from here we can easily discard those type of things, and this option will be the correct answer. Okay. Now question number 6. In this question, V is the space of polynomial function of degree less equal to 3, and T be a transformation from V to R3 like this. So here V is a0x cube degree 3 polynomial a1x square plus a2x plus a3, such that ai belongs to R. Again, the field is R. Otherwise, this is not making any sense, because codomain should be R3. Now T is defined in this way: T of the polynomial. For example, Px. If we choose Px to be that polynomial, then T of Px by definition, this is same as P of 1. So from here we can easily see P of 1 is same as, just apply, put the value here. So the value of x is 1. This will give us a0, a1, a2, a3. Similarly, P of minus 1 a0 minus 1 cube, which is minus a0, a1 minus 1 square, which is plus a1, minus a2, plus a3. P of 0, so P of 0, a0 0 cube, which is 0, a1 0 square 0, so those are 0, only we get a3. So by definition, T of px is same as a0 plus a1 plus a2 plus a3, maybe, okay, comma, minus a0 plus a1 minus a2 plus a3, comma a3. By definition, t take this form. So again, we need to see what is the null space, what is the dense space. So for this problem, it is hard to see what is the actual range space or what is the actual null space. So we need to again find null space. So let px belongs to null space of t, right? Then t of px equal to 0, but t of px equal to 0, this will automatically imply this whole thing becomes 0. So this whole things becomes 0 is equivalent to saying all those components are 0. So again, we will solve this kind of equation and see what are the possibility of AIs. 1 1 1 1 minus 1 1 minus 1 1 0 0 0 1. Just putting the coefficient, and again we'll apply. So we need to find null space. So find all AI such that this vanishes, right? So apply R2 plus R1. This will give us 0 2 0 2 0 0 0 1. Similarly, so half of R2 0 1 0 1. The above is same. This is also same. Then R3 minus, sorry, R1 minus R2, so that this vanish. So it 1 0 1 0 0 1 0 1 0 0 0. Now R1 minus R3. So this gives the row reduced echelon form, which is, sorry, R2 minus R3, because there is 1 above. So 0 1 0 1. This becomes 0 0 0 1. Right. From here we can see this is the row reduced echelon form REF. Therefore, what are all those possible solutions? What are the null space of this thing? So therefore, solution space of this corresponding thing, solution space means all those a0, a1, a2, a3 which satisfies this equation, this three equation. So again we'll see what are the free rows, right? So free rows, we can see that there is 1 1 1. So those contains pivot elements. So only free row is this. This is the free row. So in the place of free row, we can choose anything. Okay. So we'll always choose 1. Now if we choose 1, then The other thing, what are the other thing? So the last combination is, let me write what is the equivalent. So solving solving this is equivalent to solving, this is equivalent to solving this equation, x1, sorry, instead of x1, a1 plus a3 equal to 0, a1 a3. Similarly, a2 a4 equal to 0 and a3 equal to 0. Sorry, a4 is 0. So a4 is 0 is imply this must be 0, and a4 is 0 means a2 is automatically 0, and we have chosen a3 equal to 1 because this is free column. We can choose anything here, so we'll always choose 1 to get linear independent equation solution. And a3, if we choose a3 to be 1, then a1 must be minus 1. So solution space will look like this: C times something, where C belongs to 1, right? So those coefficient a0, a1, a2, a3 will take this form: minus C, 0, plus C, 0. So a0, a1, a2, a3 takes the form minus C, 0, plus C, 0. So what are the null space? Null space, we have initially chosen polynomial of this form, sorry, px of this form. Px is same as a0 x cube plus a1 x square plus a2x plus a3. So null space of T, this is a0 x cube plus a1 x square plus a2x plus a3, such that a0, a1, a2, a3, those are real number, which is same as minus C0, C0. Therefore, it is clear that null space will take this form. It will be in the place of a0, this there is minus cx cube, plus in the place of a2 there is c, so cx, right? Null space of this form, where c belongs to real number. And it is clear this is equivalent to saying that this is generated by this minus x cube plus x. So minus x cube plus x, this is the correct answer, because just add a minus sign. X cube minus x, add minus sign, this will give minus x cube plus x. So this will be the correct null space. And T is not 1 1 because x cube minus x, this is inside the null space. And range space of T is not whole R2. Is it whole R2? Because what are we seeing here? So nullity we often nullity is, this should be actually whole R3 because there is no R2. We are not identifying. So from here it is clear that nullity is 1. Therefore, what is the dimension? Nullity 1. This will automatically imply rank should be the dimension of the domain, which is 3 here, because not 3, this is actually 4 dimensional space, sorry, because it takes a0, a1, a2, a3, those are linearly independent. So x cube, x square, x1, those are basis of the polynomial space in this case. So rank should be dimension of the vector space V minus nullity, which is 3. So it was okay. Even sorry, range space of T is R2 is okay, because this is not possible. Rank of rank will be 3. So this is also wrong. Rank 3 means it should be R3, the whole thing. Okay, and null space of T is spanned by xs cube minus 1. This is also wrong because we can easily check xs cube minus 1. If we apply xs cube minus 1, apply T on xs cube minus 1, by definition, first thing, by definition here, from here, we can see that here a0 is 1, a0 equal to 1, a1 equal to 0, a2 equal to 0, and a3 equal to minus 1. So again, if we apply the definition, this gives us 0 here, minus a0 plus a1, which is minus 2, then minus a2 plus a3, sorry, minus a0 plus a1, which is minus 1 actually. Minus 1, then 0, then a3, which is minus 1. So this is not 0, right? So this cannot be an answer. So again, without solving, we can see that those two options are not possible. This is not possible because applying direct application will gives impossibility of this option. And also T is not 1 to 1. So to get other option, we can solve. We just solve and we can see that it is generated by this. Therefore, T is not 1 to 1. 1 to 1 means it is bijection. It is not even injective map because kernel contains something. Injectivity, it is only possible if and only if kernel or null space is 0. So, so this is the only correct answer. For question number 7, here T is defined as this. T is a linear operator on R3. So linear operator means it is domain and codomain are same. It is a linear transformation from V to V. So V is here R3. Then which of the following is correct? So A, the inverse of T does not exist. T inverse will look like this. So again, the following problem is equivalent to solving this. So we are trying to if T inverse exists, then we just write in a matrix form. So T inverse exists means T will, if we apply, so T, if we apply T on some matrix, for example, x1, x2, x2, x3, this will give me z1, z2, z2, z3. Sorry, z1, z2, z3, this. So again, we are putting linear in, that is in a matrix form, right? So this is equivalent to saying that the matrix form will be like this. So it is 1, 2, 3, and the next will be 2 here, 2 here, so 0, 2, 2, and minus 2, 0, plus 1. So this is the matrix form A, and again we take the augmented matrix Z1, Z2, Z3. We can easily see that this should be the matrix representation, because how to get matrix representation? We just put TE1. E1 means 1000. So TE1000, sorry, 1003 R3 it is. So this will give you 1, 0, and minus 2. 1, 0, minus 2. Just put this thing, put 1, 0, minus 2 in the first column. Right, those gives the matrix representation. So we are solving for Z1, Z2, Z3. So let us solve. So again, if we apply row reduction, then the left side will becomes row reduced echelon form. So if it is in the invertible, row reduced echelon form must be y, and again that row reduction. So once we get identity on the left side, the row reduction will lead to A inverse X. That is, this will give the invertible thing, right? The inverse. If this is if this is full rank. If this is invertible, then we'll get the inverse on the right side, and left side becomes row reduced echelon form, possibly I. So let us see what a row reduction leads here. So R3 plus 2R1, 1, 2, 3, Z1, 0, 2, 2, Z2. This is 0, 0 plus 4, which is 4, 1 plus 6, which is 7, right? And this is Z3 plus 2, Z1. Now R2, half of R2, 1, 2, 3, Z1, 0, 1, 1, Z2 by 2, 0, 4, 7, Z3 plus 2, Z1. R3 minus 4 times R1, 4 times R2, and R1 minus 2 times R2. This will give me 1, 0 here, and minus 2 means 1, and Z1 minus 2 times this. 2 times this means Z2 itself. So Z1 minus Z2. These remain the same. Z2 by 2. 4 minus 4, which is 0. 7 minus 4, which is 3. And this becomes Z2 plus Z3 plus 2Z1. 4 times this, which is 2Z2. So minus 2Z2. Now we can easily see that this is almost done. So 1/3 of R3. This will give us, those rows are same, but this is 0, 0, 1, and this is Z3 plus 2Z1 minus 2Z2 by 3, and just add R1 subtract R3, and from R2 subtract R3. So this gives us 1, 0, 1, and Z1 minus Z2 minus R3, that is this thing, Z3 plus 2Z1 minus 2Z2 by 3. Similarly 0, 1, 0, sorry, it becomes 0 because once 1 is subtracted, this becomes 0. Similarly 1 is subtracted, this becomes 0. There was 1, but 1 is subtracted, this becomes 0. Now from Z2 by 2, we are subtracting this, Z3 plus 2Z1 minus 2Z2 by 3. 0, 0, 1, this becomes, this is remaining. Therefore A inverse of Z1, Z2, Z3 this is same as just so clearly this thing. So this is, if we calculate, this is same as 3Z1 minus 2Z1, which is Z1, then minus 3Z2 plus 2Z2 minus Z2 minus Z3 by 3. This is same as, now there will be 6 below. 3z2 minus 3z2 minus plus 4, that is 7z2 here, minus 2z1, initially minus 2z1 and minus 2z3. This is same. So here the answer will be z1 minus z2 minus z3 by 3 minus 2z1 plus 7z2 minus 2z3 by 6 and z1 z, just rearrange, 2z1 minus 2z2 plus z3 by 3. So this would be the correct answer. So let me see what so inverse of this is this, but to write in the proper way, that is in the linear transformation, it will take the row form. It is, this is 3 by 1 matrix, but this should be 1 by 3 matrix, right? So 1 by 3 matrix, okay, 1 by 3 matrix of this form. So it must be, first one is z1 minus z2 plus z3 by 3. So it is not matching. So I have done some mistake. Let me find where is the mistake. Question number 7. So, oh, there is no 3. Initially, I have done a mistake. It should be 1 to 1 times x3. So, there is a slight mistake. So, it should be 1. Then 0 to 2, it is okay. Lots of mistake. This is 0 to, coefficient of x3 is 1 again. I don't know how to mistake. So if we correct those, so those are actually 1 and 1. 1 to 1, 0 to 1, minus 2, 0, 1. Okay. Okay, so if we correct, then R3 plus 2R1, this will give us 0, 4, 3. This is 0, 4, 3. Just we'll correct those steps. And this is Z3 plus 2 Z1. This is 1 to 1. 0 to 1. Okay. Now half of R2. This is 1 to 1. Those type of operation, it is better not to perform those type of operation, but for consistency, I am performing this because fraction is bad thing for our calculation. 0, 1 half Z2 by 2 and 0, 4, 3 Z3 plus 2 Z. Now R3 minus 4 R2 and R1 minus 2 R2. Yes, it is okay. So R1 minus 2 R2 will give 0 here and also 0 here. Z1 minus Z2, it is okay. Now R3 minus 2 R2, 4 R2, this is 0, 3 minus 2, which is 1. So it is now more easier. Z3 plus 2 Z1 minus 2 Z2. Yes, it is okay. Now there is no need to perform this operation because it is already 1 in the third row. And we need to perform only R2 minus R3 because there is nothing above this one, right? So I am erasing those things. Okay. So if we calculate R2 minus R3, so this is Z1 minus Z2, this remain unchanged. But after that, it is Z2 by 2 minus Z3 plus 2Z1 minus 2Z2. And this is Z3 plus 2Z1 minus Z2. Okay, so the answer should be like this. Okay, the answer will be Z1 minus Z2 here and 4Z1 minus 4Z2, that is minus 3Z2, Z3 by 2, 2Z1 rearrangement, give 2Z1 minus 2Z2 plus. Okay, so this is matching with Z1 minus Z2. So T is invertible is clear now. So this is not correct. First one is Z1 minus Z2. So there are two Z1 minus Z2. But second one is this by 2. This is matching 2Z1 minus 2Z2 plus Z3. Yes, so this is the correct answer. Answer D. Now let us see question number 9. Given T is this T is from R4 to R4. There are two linear operator on R4 and UV another linear operator. Those are defined in this. So let us see what is TU and U2 before finding range and null spaces. Okay. So UT of x1, x2, x3, x4. If we apply T first, then applying T will give. So first apply T. Application of T will give 0, x1, x2, 0. But what is U? You just taking this x3, x4 in the first second place. So here x3 means this, x4 means this. So first, so this becomes applying this in the first place, and the last will be in the second place, and other are 0 by definition of U. Similarly, TU of x1, x2, x3, x4. By definition, applying U, this will give x3, x4, 0, 0. Now applying T, what T is doing, T is just shifting this x1 in the second place, x2 in the third place, and other things become 0. So x1 in the second place, this x3 is in now second place, and this x4 shifting to the third place. So there will be x4 and other things are 0. So those are the definition of TU and UT. Now what is the nullity, and so we need to find range of tu. There are lots of things need to be done. So first, what is the rank of tu? From here it is clear that rank of tu, so any element of tu, so rank, before rank of tu, let me say range of tu. So range of tu, this is actually generated by, so any element can be written as x3 times 0 1 0 0 plus x4 times 0 0 1 0. Those are linearly independent. So this is generated by E2, the standard. Maybe let me write 0 1 0 0 0 0 1. This is tu. Therefore, rank of tu, there are only two bases in the dimension, in the range space, two basis element which generate the range space. So dimension must be 2. So rank of tu should be 2. So this is false. Sorry, this is false. Now what is the nullity of tu? Again, rank nullity theorem. So tu is a map from R4 to R4. This is the linear operator tu. From here we can see domain, rank of the dimension of the domain is 4. So nullity of tu, this is dimension of the domain which is 4 minus rank of tu which is 2. So this becomes 2. So this is also false. Now option C, what about option C and D? So range of tu is, we have already found, we have got range of tu, but nullity of tu, null space of tu. So we need to find null space of tu. So null space of tu, here in tu it is this notation. So suppose x1 x2 x3 x4 belongs to null space of tu. This will imply, this is if and only if this 0, that is tu of this x, maybe write this as x, tu of this x becomes 0, but this is if and only if tu of x, by definition this is same as 0 x3 x4 0. This is 0. So this is 0 if and only if x3 and x4 both are 0. So nullity of tu, it will consist of those matrices. x1 x3 x4 are 0. Sorry, x1 x2 are anything, but x3 x4 are 0. So xi belongs to real number. This is the null space, right? Now what is the intersection of null tu, intersection range tu? So ntu intersection range tu, but range tu will take this form, right? Range tu contains all type of matrix, all type of all of these 4 tuples. So first and fourth element should be 0, and for something belongs to belongs in null space, this will imply third and fourth entry should be 0. So third and fourth entry should be 0, and this also belongs to range space, means first and fourth entry should also be 0. So first fourth here, third fourth. So together we are getting, this is same as x1 x2 x3 x4, such that third 4 are equal to 0, and first 4 x1 x4 equal to also 0. So this is equivalent to saying 0. x2 can be anything, x3 x4 are also 0. x2 can be anything, right? So dimension of this thing, clearly dimension of NTU intersection range TU, dimension of this thing is 1. So this is one dimensional. So this is also false. So this should be the correct answer. So let us verify if this is correct or wrong. Okay, before claiming. So RUT takes this form, but what is NUT? So suppose x1 x2 x3 x4, this belongs to n of ut, right? This will imply ut applied on this x is 0, ut applied on this x is 0, but this is if and only if x2 0 0 0 equal to 0. So null space of ut, it will contain x1 x2 x3 x4, but x2 is 0, so we may cancel x2, put x2 to be 0, and xi are any real number. So again, n of ut, intersection range of ut, it will contain, so n of ut intersection r of ut, it will contains element of this form x1 x2 x3 x4. So to this tuple belongs in n of ut, it must satisfy the relation, that is x2 to be 0. And if this belongs to range of ut, then this will imply except the first thing, all those are 0. That is x2 x3 x4, those are 0. So this is equivalent to say, this is equivalent to say that this is same as except x1 all are 0. Now we can see that this element x1 is any element of it. So this belongs to range is clear. Just in the place of x2, just replaced by x1, and this belongs to null space is also clear because the second coordinate is 0 here, right? So from here it is clear dimension of NUT intersection RUT is 1. So this is correct answer. So from here you can observe that, just a minute. From here you can observe that null space and range space may intersect. So it is not necessary that null space and range space do not intersect. They may intersect. Okay. So question number 10. In this question, V with the vector space of 4 tuples over F. So V is of this form x1 x2 x3 x4 belongs to F4, 4 tuples, and T is linear operator on it. So T is a linear map from V to V. And there are four linear operator is given. We need to find operator for which rank of t is same as half of rank t square. So let me see what is t square here. T square x1, x2, x3, x4. This is same as t applied on this. T applied on x1, x3, 0, 0. So again, if we apply t, what is t doing? T is taking third element and putting here, right? So it is x1, 0, and except those, everything becomes 0. Similarly, t square, if we apply t again, then we are getting t square x1, x2, x3, x4. What is t doing here? T is putting fourth entry. T is putting fourth entry to the first place. So let me write it. This is same as t of x4, x3, 0, 0. But fourth thing is 0 here, so it becomes 0. First entry will become 0. Again, we can see that third entry is 0. So third entry, t puts third entry into second place, so this also 0, and rest of the thing are 0 by definition. Similarly, this t square x1, x2, x3, x4, so similarly we can calculate, right? Now rank of t is same as half of rank t square, but this implies that since rank is integer, this implies rank t square should be even, right? Otherwise this is not possible, because if rank t square is odd, this will imply rank of t is fraction, which is not allowed. Rank is always integer. Similarly, here we can see that t square of x1, x2, x3, x4, what will we get? So t is putting x1 in the last place. So here first entry is x2, so it will put x2 here. T puts x2 in the first place. X2 is 0 here, so again if we apply t, 0 will be in the first place. T puts x3, t does not put x3 in any place, so x4 goes to fourth element goes to third place. So here fourth means x4, fourth means x1, it goes to third place. Third place means here, right? And this is 0 by default. Similarly, for this, if we again apply t on the both side, then left side becomes t square, x1, x2, x3, x4. The right hand side becomes, so here t is shifting these coordinates. So it putting 0 in the first coordinate and shifting everything else. So it is already shifted. Now it will again shifted. So 0, 0, x1, x2. Sorry, it is not completely shifting. So this is same as t0, x1, x3, x4. But by definition of this t, this is same as this x1 goes in the second place. So here x1 is 0, second place becomes 0, and first place is 0 by default. Now x2 does not go anywhere. x3 in the third place, x4 in the third place. So x3, x4, those remain in the same place. So those are t square. Now let us see what are the rank of t square. So you can see that rank of first t square here, rank of t square is 1 because it is generated by those kind of element. It is generated by E1, standard element E1. Similarly, it is 0, so rank of t square is 0. Here rank of t square is actually 2. Rank of t square is again 2. But this rank t is actually 3. Rank t is actually 2, 3. Rank t equal to 2, rank t equal to 2. So those two is cannot, those two are not possible because rank t must be even. Oh, sorry, rank t square must be even. So it is, we cannot conclude this. So which of the following satisfies the relation rank of t is same as half of rank t square? So you can see half of 2, this is 1, half of 2 is 1, half of 0 is 2. Sorry, I think the question should be like this. So let me modify the question. Actually, this is not possible because rank of t square is always less than rank t, less equal to rank t. So the question should be like this. This is 2 times rank t square. Okay, that is rank of t is even in this case. Then first two options are not possible because rank are not even. But here we can see rank t square is 0. So 2 times rank t square should be 0. So this is also not possible. This is not 0. In this case, rank of t square is 1, rank of t is 2. So this is a correct answer. Right? Okay. So let us solve another question based on linear transformation. Maybe try some question from open college. So consider this question. V is generated by this basis alpha 1 up to alpha n, and T is a linear operator on V such that T of alpha j equal to alpha j plus 1. This is true for j equal to 1 up to n minus 1, and T of alpha n equal to 0. Then question is, what will be matrix representation of T with respect to this basis? With respect to this basis, sorry, this is B, and V equal to vectors space generated by B. Question: what is the matrix representation of this T? And so let us see what is the matrix representation. So we can see T of alpha 1 is same as alpha 2, right? So we can write this as 0 times alpha 1 plus 1 times alpha 2 plus 0 times alpha 3 up to 0 times alpha n. Similarly, T of alpha 2 is same as alpha 3. 0 alpha 1, 0 alpha 2 plus 1 times alpha 3 plus 0 alpha n. Similarly, up to alpha n minus 1, everything continuous, everything can be done in similar manner. This is 1 alpha n. And now T of alpha n is 0. So every coefficient are 0. Therefore, matrix representation of T with respect to this basis alpha 1 up to alpha n, this is just take the coefficient and write in column, right? So coefficient of the first thing is 0 1 0 0 everywhere. The second thing is 0 0 1 and 0. Similarly, it will continue 0 0 0 1, and the last thing, everything is plus for the last alpha n. So this will be a matrix, and this will be the matrix representation of T with respect to this basis. Now question is, another question, can you see T to the power n equal to 0, but T to the power n minus 1 is non-zero? So let me show if this is true or not. So what does T alpha 1 up to alpha? So if we apply T, then this becomes alpha 2, this becomes alpha 3, alpha n minus 1 becomes alpha n, and alpha n becomes 0, right? This is first application of T. Then if again apply T, by definition alpha 2 goes to alpha 3, alpha 3 goes to alpha 4, and alpha n goes to 0, right? 0, this goes to 0, 0 always goes to 0 under linear transforms. So if we continue this process, then this is application of T, this is T square. So T compose T, it is equivalent to having T square. So if we apply T to the power n minus 1, then alpha 1 goes to alpha 2, alpha 3. In this way, this goes to alpha n. It will first application, it increase 1 to 1 plus 1, that is alpha 2. Second application, it will increase 2. Third application, it the indices is increased by 3 like this, right? So n minus 1 application increased by n. Similarly, t to the power n minus 1 alpha 2. This is same as t to the power n minus 1 t alpha, because alpha 2 means t alpha 1, right? But t alpha 1 so this is same as t to the power n alpha 1. But from here it is clear that t to the power n alpha 1 is 0. So this is 0. Similarly, you can prove t to the power n minus alpha 2, n minus 1 alpha 3. This is same as t to the power n minus 1 t alpha 2. But it is clear this can be written as t composed to the power n minus 1 alpha 2, which is 0 by the first thing. Similarly, after this, all of t to the power n minus 1 alpha n will be 0. So clearly, t to the power n minus 1 alpha 1 equal to alpha n, which is non-zero because base is element. Hence, t to the power n minus 1 is non-zero because if it sends alpha 1 to something non-zero, so it cannot be identically 0 transformation. But t to the power n applied on anything, as we have seen, t to the power n alpha 1 equal to 0, so it will automatically imply t to the power n any alpha is 0. So t to the power n alpha equal to 0 for all alpha, right? Therefore, t to the power n equal to 0. It also can be seen as just multiplication of those matrices. If you multiply n minus 1 times, this row just comes in the first place. So sorry, this column comes in the first place, t to the power n minus 1. But if you apply t again, t to the power n, then this row vanishes. So everything becomes 0. So we can see that what is t doing? It is just shifting a row in the front, right? Shifting the second row to the first place. Consider the identity matrix. T is just shifting the rows in a previous row, right? So this is solution for this kind of problem. Okay. So I think this is enough for today. Again, we'll meet in the next week. Thank you.